Yes, just a minute. I'm just checking the number. Question number. AQ 10.6. Just a minute. I'm just opening the number. Yes, AQ 10.6 question 3. Suppose we obtain the following BFS that I'm asking.
Okay, so um, we've discussed this in the class, right? The last class that we had, the summary section, we discussed the type of edges that a BFS tree can have. So you can just look at it's there in the last session. We
I'm
discussed it
actually,
in
I
detail.
was trying to ask only one thing, means, uh, as you had also once advised that I think that suppose we have to check for every option. Like suppose AE is an edge in the original graph, then considering AE as an edge in the original graph, we have to perform the BFS and then check whether the same tree is coming. Is that right?
Okay, just give me a minute and I'll just tell you how it's done. One
Means
minute.
a particular doubt I have. If you
Let me just
confirm, I
share
will
my
ask.
screen. Is my screen visible?
Yes, ma'am.
Okay, so let's just say that you have a BFS. How do you tell if there is an edge or not? What happens is you just tell if, let's just say in the question that you are asking, if you have to check if there is an edge from A to E or not. So here you have A on the initial level, and then you have BC on the first level, and then E is here on the second level. So if there was an edge from here to here, you see E here on the first level, which is, it's not here. That's how you identify it. So A and E cannot be an edge, because if it were an edge, you would see E here on the first level. Do you have any specific doubt, or was this your doubt? That's how you check if that's an edge or not.
Means the method now told. Could you please actually explain it just briefly? The method. I was actually checking for every option, but that was taking long. This method, could you please just tell once?
Okay. So when you make a BFS tree, what happens is you just mention it's unique, obviously. So what you do is you mention all the edges that are directly on the
Ma'am, your
first level.
voice is
There are
very low.
edges.
Sorry, ma'am.
Is it better now? Can you hear me?
No, ma'am. Yes, ma'am.
Am I audible now?
Yes, ma'am.
Okay.
Yes, ma'am.
What you do is if you start your search from A, so this is the vertex where you start your search from, and this is the first level. So first level basically means all the vertices that are directly connected to A via an edge. There should be an edge here. So if there is an edge from A to E, you'll see E here, because that's how you do. That's first you write down all the vertices that are directly connected to A via an edge, and you mention them on the first level. So if you don't see E on the first level, that means A and E is not a direct edge in the original class. That's why you don't see it, and you see it somewhere here on the second level. This is second level. Is it fine now? So A and E can't be an edge in the original graph. When you talk about A and D cannot be an edge, because if D was an edge, you'd see D here. The same reason.
Means the method is we have to write all the.
AE can't be an edge because you don't see it
And
on level 1. AF, yes, AF can't be it. AD can't be
won't
an edge.
A be first level and BCE second level?
So no, it really doesn't matter. You're not going to be asked. This is considered to be 0th level or something. But the first level starts from here, generally.
Ma'am, actually, I was having some connection issue. While you were speaking, I could not get the audio clearly. Means I could see the diagram. The method could you please tell means how we identified. Sorry, ma'am. Actually, I was facing connection issue.
So this is how your graph looks like. Right? So what you do here is this is D. So A and E cannot have an edge. So you understand why these two cannot have an edge. A and E.
Yes, on that
Okay.
method, how to understand that you told, that method I am asking actually, instead of checking all the option that you told now.
Method, you don't have a method for it. That's the method. If you see them on the same level, if that's how you check, you'll have to check for each option. There's you can't actually figure out the original graph. If that's what you're asking, you cannot figure out the original graph just by looking at the tree. That's
No,
not
no, I am
possible.
not asking about the original graph. I am asking that question only. Means AE is not an edge. That how you understood that method.
Okay, I'll repeat it again. If you don't see, if if A and E, so every vertex that has a direct edge to A, you see it on the first level. That's where you know how to make a DFS tree.
Yes,
You do know that, right? So what are the first level vertices? They are the ones that are directly connected to A via
yes.
an edge. If
Okay.
E were connected to A via an edge, you'd see E on the first level, but it's on the second one, right? It's on the second level. It doesn't have a direct edge to A. Otherwise, you see it here. A and F cannot be an edge because otherwise you see F here on the first level. A and B cannot have an edge because otherwise you see it here. B to be on the first level. And about B and C, so if you look at B and C, they can have an edge because they're on the same level, so they can have an edge. Even if there
So
was an
that
edge, you can't
the
make it in this.
vertices that have the same level, they can have an edge.
Yeah, that's there are other rules too. So if they're on the same level, they can have an edge. If let's just say you have something here, and then if you're asked if D and G have an edge, so D and G are not on the same level. This is the second level, this is the third level, but they still can have an edge. D and G can have an edge too. We've discussed it in the summary session. That's
Okay.
why I'm asking you to check them in detail.
Ma'am, B and D, ma'am, B and D looks like they are on same level, but can it have an edge? B
They're
and D.
not on the same level. This is on the first level. This D is on the second level. So if B and D can have an edge, not because they're on the same level, but because okay, if D and B had an edge, you'd see D here. Let me just tell you how you make a BFS tree. Start from here, and then you see
Can
directly
we say
connected
that
edges, B and C.
there's no forward and back edges in BFS 3?
Sorry, what?
There is no forward edge and back edge in forward 3. BFS 3.
No, the BFS tree we don't discuss about forward edge, back edge, and all of that is the concept from BFS tree. So we don't talk about the concept of those things here in the BFS tree. They're
So, ma'am,
defined
A
for DFS trees. You discuss those things in a DFS tree, not in the BFS search. You don't need them here. So the ones that are directly connected to A, you write them here. Then you go to B. That's how your BFS works.
Is
Because you
from the B
entered
we
this
will
thing
write out
first.
all the
Then
connected
yeah,
vertices.
the directly connected ones you write here. Then you
Yes.
move to the C1.
Yes.
And then you write the directly connected ones here. So if this thing and this thing had an edge, wouldn't you write it here? Let's just say you have an F here. If B and F had an edge, you'd write it here, right?
Okay.
That's how you check it. So if you know how you make the tree, you'd know what edges are there in the original graph.
Okay. Thank you, ma'am.
Ma'am, can we start summary now?
Start with the summary now.
Yes, ma'am.
We'll start with the, you're done with topological sorting, right? So we'll start with the transitive closure thing. I believe that's the first topic that's there in week 11. So transitive closure, what does it actually mean? So when you have a relation R, say, and you're defining a graph according to this R. So whenever you have a graph, you must know that there is a relation as well. And that's how you define. So if these two vertices are connected, you are connecting them using a relation, right? So this edge represents a relation. You are making this edge according to some relation that you must have defined on, right? And the so in a normal graph, when you look at some normal graph, say you don't have it to be transitive, right? So if you have a graph, it doesn't have to be a transitive relation. So graph in a way is, if you have these things, say, then you can look at the graph in the context of relations too. So if there is an edge between these two, that means these two are related. If there is an edge here, then these two are related. But this is clearly not transitive, right? Because when you have an edge from here to here, that means these two are related. These two are related, but you don't have an edge from here to here. For this to be a transitive relation, you need, if there is an edge from this point to this point, from this A to B, and then there is an edge from B to C, then there should have been an edge from A to C as, which you don't see. For example, let's just see. So what you do here is, and this is in graph theory, you call this thing as an ancestor. So C is called an ancestor of A. And when you have things directed like this thing, then it becomes more clear. Then C is an ancestor of A. Otherwise, even if it's an undirected graph, you can call it to be the ancestor of this. But what happens here is that this relation of this is not the relation that you already have here is not a transitive relation. That's the problem. Because we've already seen there's no edge from A to C. So what you do is you try to make this relation transitive and you denote it by R. So how do you do that? You just say that if there is a path from, so R plus we define as, so R is the relation that you're using here. So I hope you do understand that there is always a relation when you have a graph, an underlying relation. These two are related. And then you just figure out an R plus, which is the transitive closure, which would lead to the transitive closure of this. So if you want to find the transitive closure of this, what you do is take the underlying relation and then you just make it transitive. So this is the underlying relation. And then you make this thing transitive. So how do you do the transitive thing? We know that if AB is an edge and BC is an edge, for this to be transitive, we want AC to be an edge too, right? So what we do here is, okay, let's just uh, let's just first see the R relation. So R relation is AB is a thing. These are capital here, but I'm right. AB is a thing here, then BC is here, CD is here, DE is here. It's an undirected graph, so the direction really doesn't matter. That's it. Make it transitive, what you do is you see that AB and BC is here, so you should add. So to make it R plus, it's obviously R, and then you union it with, because I don't want to repeat writing this thing again, so I'm just writing R simply here. And then, so what edges should be here to make this thing transitive?
Ma'am, BC and CE.
BC should be here, and then CE should be here. That's it. So you add these things to it, and then
Ma'am, BC is already there.
okay, if it is there, then
Ma'am, it's AC.
okay, yeah, it's AC.
AC and
To
CE.
make it transitive, it's AC and CE that are needed. Then this becomes transitive. So that means you change this graph to, you join these two things, and you join these two things. Then your graph becomes transitive of what you already have. This is your uh, transitive thing, uh, which is one topic. And to find the
Ma'am,
transitive closure, because here you can just check it from here by, okay, just give me 1 minute. You can just check it from here because it's a very simple graph that we've seen. But sometimes what happens is you can do it by using BFS, DFS. How do you use BFS and DFS to find the transitive closure? So
Ma'am, so
What
when
does
we do the
BFS
R
help
plus,
with?
hello,
Yes.
when we try to do the R plus, we should do the union with R and consider
Okay,
that.
wait, give me just 1 second. This isn't done yet because if you have an edge from A to C, you have an edge from C to E, so there should be an edge from A to E as well. So you should have an A to E as well. What we're trying to do in R plus is you have edges already here. You just want to make sure that if, so in R plus what you do is if, so AD, let's just say AD. So AD would be an edge in R plus if there is a path from A to D. Is that all right? In simple words, R plus is the collection of all the edges. So if A and D, A has a path, there's a path from A to D according to this relation, then in R plus relation, there'll be an edge from A to D. That's the simplest way to look at it. Is that all right?
Ma'am, are we not making it like a cyclic, like all the cycles should be closed?
Yeah, all the cycles should be closed. That's one way to put it. Yeah, you can also say that, but the if you have to put it in like simpler words, it will be if there is an if you see, so it's, let me just write it here. So AI and AJ is an edge in R plus, that is the transitive closure, if and only if AI has a path till or a path to AJ with respect to R. This is it. This is the simplest way to check it. So if there is an edge from AI to AJ, then there is a path from AI to AJ in R. Or if there is a path from AI to AJ in R, there is an edge from AI to AJ. And then one way to do this thing is the BFS DFS approach you can use. So BFS, what is BFS used for?
Shortest path, ma'am.
In the last class we discussed this. It is used for majorly. There are obviously other reasons too, but uh, the most, the first thing that comes to your mind is reachability, right? To check the reachability of a
Then
vertex
this
from
R
another
set we are
vertex.
writing, those only belong to the original graph, and R plus we are writing, we are trying to make the transitive closure.
Yes, because if you make this an edge, then it will be a transitive closure. No? This thing, what you're saying is that if this was a path, this is a path here. From A to C, you have a path. You don't have a direct edge in R. But in R plus, you make it an edge there from A to C. So if you see an edge from AI to AJ, a path from AI to AJ in R, then there is an edge from AI to AJ in R plus. In
Okay.
very simple words, it's this one. And then about the BFS, how can you do it? So BFS is used for reachability purposes, where you can reach. There are other reasons too, obviously, but one of them is reachability. First reason, obviously, is reachability, to see if you can reach from AJ to which vertices can you reach. This is what we've discussed in the last summary session too. Which are the vertices that you can reach from AJ? That's what reachability uh, is, and that's why you do BFS and DFS. That's one of the reasons. So what are you trying to find here? You're just trying to find if there is a path. So you've written here if AI and AJ has a path. That means you want to see if you can reach from AI to AJ or not. That's what a path means, right? So give me a minute.
Excuse me, ma'am.
Yes.
Ma'am, the part of transitive, the meaning of transitive you explained, understood it. But its relation with transitive closure point, please explain that part again.
Okay, in very simple words, when you try to find the transitive closure of an already given graph, what you do is you have the graph, and that graph is not necessarily a transitive graph. So you know what transitive means, right? So if there's an edge from A to B, an edge from B to C, then there should be an edge from A to C. Every graph does not follow this rule. So what you do is you try to make another graph from the given graph, which is transitively closed. That's all. And that's how you do it. This is the way you do it. You just need to follow this thing.
Okay, ma'am.
Is there still a doubt?
Ma'am,
Yes.
and this transitive closure, that is, if there is edge from A to B and there is a edge from B to C, the transitive closure states that there has to be an edge from A to C, or there has to be a path from A to C.
What's written here? It's written an edge, right? In R plus, you need an edge. So if you're taking the transitive closure, it's simply if you just have a path from here to here, from A to C, then what you do in transitive closure is you consider this to be an edge. You consider to be this to be an edge. Is that okay?
Means in transitive closure the set we will consider S to be an edge.
Yeah, and this will remain intact. So if you want to, do you know how to make a set transitive?
Yes,
If there's a relation and how do you make
yes,
it
yes.
transitive? That's how it works. That's how we discussed it. So you just want to make sure that your R plus is a transitive state. That's it.
Okay.
If you write it this way, but it's not a very simple approach. This one's not a very good approach to follow. So what you do is you do BFS and DFS approach. Because if you want to see that for there to be an edge from AI to AJ in the transitive closure, you'd need a path from AI to AJ in the original graph. Is this part clear? This is what I've written here.
Okay.
Yes, ma'am.
Okay.
Yes, ma'am.
If you want an edge from AI to AJ, you need a path from AI to AJ in the original graph. And to find it, there is a path from AI to AJ not. That's what reachability do, right? That's what reachability does, and that's one way to do is BFS approach. So you can do it by BFS thing. So you start with A, let's just say you start with AI, and then you see all the vertices that are reachable from there, AJ1, AJ2, you write down all the vertices there. And then there would be a direct edge in R plus in the transitive closure from AI to AJ1, AI to AJ2, and so on. Is this part clear? And similarly, you do the BFS thing for every vertex. Is this much clear?
You are talking about the transitive sets. Could you please explain the part? I'm sorry, I also joined a bit late about that. You're explaining that you just mentioned to someone about the transitive sets. And also
I think you can
here,
just
I'm
watch
not
it
clear with that.
when it's
If you could,
uploaded, because we've discussed it for a very long time. It's been half an
yeah,
hour. We're discussing the same thing.
okay, fine.
It's
And with
nothing.
regard
It's
to this
just
part,
this
this
thing.
particular part, you,
It's just this thing. If there is a relation, so you do understand that there is a relation associated to every graph, right? Without a relation, the graph
yeah,
cannot exist. So if
okay,
AI has a path to AJ with respect to this relation. So when you say this relation, you mean that there is a path from AI to AJ in this graph, in the graph associated to R relation. Then there will be an edge from AI to AJ in the transitive closure of that graph, which you denote by the relation you denote by this, and the graph, the transitive closure of the graph you denote by this. Is this fine?
yeah. And the example that you showed from A to C, the path that was there. So is it like when I want to in terms of transitive, it's like a physical thing that I can think about from A to C, or it's like a kind of the what do you call the virtual ones that I should assume there is an edge from A to C.
If this was the original graph, then what you can do is in the transitive closure, if there is this thing, you can close this thing here. So in the transitive closure,
Okay.
you'd see this edge too. You'd see this edge too, because this is also, there's a path from A to D. That means there should be an edge there.
Okay.
And then there are others left too. You can make one from B to B as well.
Okay.
So you'll have to see. So that's why there is an approach for it, because there are just 4 vertices, a simple graph, and we're still not very comfortable with how to make it. So we use approaches for it. One of it is BFS and DFS, obviously, because these two help in finding the reachability from a particular vertex to some other vertex. So that if AJ1 is reachable from AI, that means this is in R. If AJ1 is reachable from AI, that means there's a path from AI to AJ1 in the original graph. So in the transitive closure of that graph, you'll see an edge from AI to AJ1. That's all that you need to know about this thing. And then we have the matrices for it. So, and we'll see how to make the adjacency matrix for this R plus thing as well. We'll come to that in a while. So what you do is, so A plus is the matrix associated to adjacency matrix, you can say, of transitive closure. Or if I forgot to write one line here. Adjacency matrix of, say, a graph G, then A plus you denote with adjacency matrix of your transitive closure thing. So we'll discuss how you find A plus, but before that
Excuse me,
we'll
ma'am.
discuss, yes.
And since my audio is going bad, I have sent this only in the chat. Could you please confirm once if I understood it correctly? I have sent in the chat, meeting chat.
Okay, it's almost correct, but the A to C is not a transitive closure, it's an edge in the transitive. Transitive closure is the new graph that you get.
Okay, ma'am. Ma'am, transitive closure the set of edges we write there, so that are not originally present in the graph. But if they were present in the original graph, could we write them in
You
the
would
set of?
have to write them. In the transitive closure, you write the originally. We've done it here, no? We've written that's why we've used this thing. The union and already present in our,
Okay, so union with the original graph.
yeah,
Means
the extra edges
in
that
this
you add
example,
and then the original graph.
in that example, actually AC and CE were not there in the original graph.
Yeah, they were not there, but they're in the transitive closure. We were trying to make the transitive closure here.
No, just my simple question was if they were originally in the graph, so could we make that into the transitive closure? The just
It
like
is
before.
in the transitive closure. This is the transitive closure, and you include this part as well.
Okay. Okay, ma'am.
Okay. So we'll first discuss the A. This is one thing. We're talking about the matrix multiplication, but first we'll see how we do this thing. So A1 basically is the adjacency matrix for some graph, say this is your graph, and this is the adjacency matrix for it. Let's just say it has three, let's just keep it three only. Let's just say it has three vertices. We know that the diagonals are zero, and then let's just do this. So let's just say this is your graph. That means this is your vertex 1, 2, 3. The same thing here. So I hope you do know how to read this thing. And then what you do is, what does A square represent? And how do you even find A square? So A square is basically, this is if there is a direct edge from B1 to B2. So if there is an edge from B1 to B2, you keep a 1 at Aij. Aij becomes 1. And if there isn't an edge, then it becomes 0. So this just simply means that if there is a 1 here, that means B1 and B2 are connected by a direct edge. Otherwise, they're not. That's what this thing means. What does this thing mean? This thing basically means if you just go to B1 and B2, let's just say you do B1, these things stay the same here. So from B1 to B2, you include, this is when you have a direct path from one direct path, not a direct path, when you have a direct edge from B1 to B2. And this is basically when you have a path from B1 to B2 of length 1. So this is the path from B1 to B2 of length 1, where you would include one thing there. It could be anything. It could be some Bj. So it's basically B1 to Bj and then Bj to B2. And if there is some Bj such that there is a path, there is an edge from B1 to Bj, and then there is an edge from Bj to B2, then you write 1 here. And if there is not any path, any edge which follows this thing, if this doesn't happen at all, then you put a 0. Let's just look at this thing. If you want to find V1 to V2, so what you can do is you can go from V1 to V2. So there is a direct edge from there. if you have a direct edge from V1 to V2, and then you want to find if you can go through something else, some Vj. So from V1 to V3, you have a 0 here. That means you can't do that because you can't take V1, you only can take V3 here. There can just be V3. And from V1 to V3, there's no edge. That means you can't go from V1 to Vj and then V3 and then V3 to V2. That means there'll be a 0 here. So from V1 to V2, it's a 0.
Ma'am, can you please explain this again?
Yes, ma'am. Can you explain it again?
Yeah, sure. What we do here is in this thing, how do we look at this? Firstly, a 0 represents that there is no path from here to here. No path, not a path. It's I keep using the wrong word. It's edge. So this means that there's no edge from V1 to V1. Then there's an edge from V1 to V2, and this means there's a 1. And then there's no edge from V1 to V3. This is what this means. So when you come here, what you do is you don't want a direct edge from V1 to V2 this time. What you want is you want a path from V1 to V2 such that there's only one vertex between them. So it's this thing. First from V1 to Vj and then from Vj to V2. And this Vj could be anything, but in this particular example, it can just be V3. You can't have a V1 here because you can't repeat vertices here. There's no point of saying V1 to V1 and then to V2 because we don't consider this thing at all, right? So we can only take V3 here. There's only one way. But if there was another vertex, say V4, then we can also take a V4 here. So you check for, then you will have a V4 here too. So you will check if there is. So first you check if there is an edge from V1 to V2, V3, and then from then to V2. And you will check from V1 to V4 and then to V2. So that's how you check it. If you find any of these true, if say you find there's a path from V1 to V2 via V3, then you don't need to check this because you just wanted to find if this is true. So this, when you have okay, I think it's getting a little confusing. Let's just say there is a 1 here. What does this mean? It just, having a 1 here simply means that you have something in between these two things. That means you can reach to V2 via Vj. There's one more vertex. That's what it means. So how do you check it? You go to the original graph, you see if you can go from V1 to V3 and then to V2. Because V3 is the only possibility that you can have here, right? You can't have a V1 here, you can't have a V2 here.
So which means if we were looking at the matrix A3 and if there was a 1 against V1, V2, which means there were two edges between V1 and V2, is it?
Yes, yes. We'll go to that later. It's this thing there. So when you do A3 thing, you are actually looking for this thing to happen. And how do you look for it? So let me just.
Excuse me,
And
ma'am.
I'm still confused with this A2 matrix, ma'am. Can you just show an example where I will know?
We'll do this example.
Ma'am, here,
Let's
how
just.
are we sure that there will be a path from V1 to V2 via V3 in the A square?
We're not sure. That's what we're looking for. That's what this matrix is for. If there is a path from V1 to V2 via some other vertex, then you put a 1 here from V1 to V2. This having a 1 here means that you have a vertex, you have this situation happening in the graph. That's what having 1 means here. Having a 0 here means that there is no vertex, such that there's an edge from V1 to that vertex and then that vertex to V2. That's what we see. That's what A square represents. Is this fine? Let's just do this example first. So when you want something so you want this situation to happen. An edge from V1 to Vj. Vj could be anything, and then Vj to V2. But if you look at it, you technically can't have Vj equals to V1 and V2 because they are the end vertices. You can't repeat it here, right? That's not how paths work.
And so if this is the condition, that then in the A1 matrix, wherever there is 1, there should be 0 because there is 1 if there is a direct edge.
Let me just finish first.
Okay.
If you keep asking things when we're not done yet, it will get more confusing. Let me just finish this thing first. So if you want to see there's something from V1 to V2, that means you have a direct edge how many possibilities are there. First, see how many possibilities could be there. It could either be, if you want to go from V1 to V2 via one vertex, it could either be V1 to V3 and then V2. So there's one way, this is one way, and the other way, there's no other way. But if you had a V4 here, let me just say you had a V4 here. We're just considering this thing for now. If you had a V4 here, then you would have other possibility too, from V1 to V4 and then to V2 again, right? So you would have these two possibilities then. There's only two possibilities in the four vertices. If you want to go from V1 to V2 via a vertex in between, then it will be either V1 to V3 to V2 or V1 to V4 to V2. So if any of this is true, if this is happening, then you put a 1 there. If this is happening, then you put a 1 there. If both of them are happening, then you put a 1 there. But what does 1 represent? It just represents that there is a path from V1 to V2 via one vertex. So if any of them is true, if this is true or this is true or both of them are true, then there's a 1 there. And if none of them is true, you put a 0 there. Is that okay? Is this example okay with everyone?
Yes, ma'am.
Yes.
Okay. So that's how you check. And then what you do here is you're essentially, so one way to construct is you look at this thing and you go, you just need to find this thing. You just need to see if this thing is true. So you go from V1 to V3 and there is no edge from there. So there's no edge from V1. And for this to be true, just look at this thing. For here to be a 1, you would want these two to be true simultaneously. So you put a, not simultaneously, you would need one of these to be true. Only one of these. Both of them can also be true. Then also you'll have a 1 here. And for this thing to be true, that is for there to be a path from V1 to V2 via V3, what you would want is, you would want a direct edge from V1 to V3 and a direct edge from V3 to V2. So you would want both of these two to be simultaneously true. That means you would want V1, V3, this thing to be 1, and then V3, V2, this thing to be 1 as well. So this is 1, you have a 1 here, V3 to V2 thing is 1, but V1 to V3 is not 1. That's why this is not true here. So in this case, you'd want both of them to be simultaneously true. That's when you have a path from V1 to V2. And here you want only one of them to be true. That's what is necessary. If both of them are true, then also it's fine. So you put a 0 here because there is no, when you don't have a V4 here, we just consider it to make things clearer. Now you don't have a V4 here. If this is the thing, then since there is no path from V1 to V, no edge from V1 to V3, you can't have a path from V1 to V3 to V2. Right? So there'll be a 0 here. And then you have, this is already 0. Diagonals don't change. And then from V1 to V3, so you'd want one path from V1 to V2. So there's one path, there's one edge from V1 to V2, direct edge. And then you would want V2 to V3. So there's also one thing from V2 to V3. So you have a 1.
Ma'am, there's a connection from V1 to V2, and then there is another one from V2 to V1, right? Back. So does that mean in A2, in V1, V1, it should be a 1, right?
Okay, we don't count that thing. We just count it to be 0.
Okay, okay.
This is basically what we're doing here is we're trying to find the transitive closure via using this method. We'll see how we do this thing. And then when you look at, similarly, you do the A cube part, the A3 part, which is you look for, so if you want 1 here, let's say there is V2, and then you have a matrix here. So if you want a 1 here, what you want is, so 1 here basically means that you have V1 and then you have a Vj here, and then from Vj to Vk and then to V2. This is what it means. So you're looking for this thing. So what you do here is you look for a path of length 2. So this is a path of length 2 from V1 to Vk. And then you have and then you look for a path of the path of length 1, which is basically just an edge from here to here. So what you do here is, now you will consider these two graphs. So if you have these two things, Firstly, you were just considering this thing. To construct a square, you just need a1, a to the power 1. But to construct a cube, you need both of these things. Or you need a1 repeated 3 times. So one thing that you can do is, if you want to find if there is an edge in a cube here from v1 to v2. One way to do it is you go v1 to v2 via, first you look at one edge, there's one, and then you look at v2 to v1, there's one, and then you look at v1 to v3, but there's nothing there. So you can't go from, wait, we were looking for v1 to v2, right? If you're looking from v1 to v2, and you can't have this thing here at all, because there are only 3 vertices, right? So you can't have, this cannot even be a case here. For this, you need at least 4 vertices to be in the graph. All we're trying to do here is, and I'll just give you a brief of what we're doing here and why we're doing here. So one way to do things is you just check if there's a path from here to here or not. So to check this thing, what you do is, in this example, this thing is not possible. Going from v1 to vj, then from vj to vk, then from vk to v2 is not possible because you only have 3 vertices here. So in this example, this case isn't possible. So you don't construct this thing, you only construct an a square. But if you were to calculate for, say, 4 edges, 4 vertices graph, then how you do it is, you first look for, so what does this, okay, let's just see how much have you understood. What does this thing represent? I want someone to explain what this thing represents and then what this thing represents.
Ma'am, first matrix represents all the edges between v1 and v2 and v1 and v3, etc.
Yeah, direct edges, right?
Direct edges,
and then
yes.
what
And
does
then
this represent?
Here we are looking for a midpoint or a mid vertex, whether we can go or not. So first we'll check whether there's because in the above graph v1 to v2 is 1. So
you
now
don't
we
have
will
to explain everything. You just have to tell what this thing, what does a 1 mean here? If you have a 1 here, what does this mean? That's all.
That means
It
there
means a
is a
distance
path
of
of
2.
length 2 from v1 to v3.
Not of
A
length,
distance
yeah,
of 2.
a length 2 path. That's correct. And then when you come here, you need a path of length 3. So in this thing,
3.
you need a path of length 3. So how do you do it? You just check things from here. So you can apply either of them first. So what you do is, you first look if you want to find it from v2 to v3. Let's just say v4 is also here, but because otherwise it's not even possible to do the a cube thing. A cube won't be possible to construct if you don't have a v4 edge here. So what you do is, you go from v2 to, and you need to find if there's something from v2 to v3, say, this thing, or v1 to v2, say. So in v1 to v2 case, what you do is, you look for, if this means that there is no path of length 2 from v1 to v2. So you can't go from v1 to v2. If you had a v2 here, let's just say you're skipping this part. What you do is, you can just skip this thing, right? You can just say that we want v1 to vk length 2, and then from vk to v2 length 1. You can directly do this thing, right? Why do you even need this thing? Let's just skip this part. So what we can do is, we check from v1 to vk. So there's only v3 here. Vk, again, it's now reduced to the same thing that we have in the first one. Remember, we just have one thing here. But in this case, it's of length 2. So you just check if there is a length 2 path from v1 to vk or not. So this could be either v1 to v4 to v2, and then again v1 to v3 to v2. So you first go to v4 and then check here if there is v1 here, right? So if there's something from v1 to v4, let's just say there's 1. That means you have a path of length 2 from v1 to v4. So you have a 1 here, and then what do you want? From v4 to v2, you need a path of length 1. So you look at this one. So from v4 to v1 or v2? V2, you need a path of length 1. So you want a 1 and a 1 here simultaneously. Either you want this thing, or you want v1 to v3. So you want a 1 here. v1 to v3, there's already a 1 here. And then from v3 to v2 here in this one. Check for v3 to, because it's of length 1, right? So V2 to V3, you have a 1 here. So either you want a 1 and a 1 here to go from V1 to V3 and then V3 to V2. This is it, V1 to V3 and then V3 to V2. Either you want a 1, 1 here, you want this to happen simultaneously. Both of them should be true. Or you want this thing to happen. That is from V2 to V4. So you want V2 to V4 to be 1. Here you want a 1. And then V4 to, we're going from V2 to V. So you do understand what I'm saying, right? I just forget the vertices over and again. V1 to V2, if it is, then you would want V1 to V2. So you would want one thing to be here. And then V2 to V4, one thing to be here. This one we've already done, right? Is there a confusion? Because I have to come back to this thing and then mark everything here. Is it understood, or do I need to repeat this thing?
And somewhat we understand it.
I don't think it's clear. See, it's
Not
not
that
that
much.
important, but whatever we've discussed so far is not that important, but we're still discussing it. So,
Excuse me, ma'am.
yes,
Ma'am, do you have any question on this concept?
I don't think there are questions on these one. That's why I say that this is not that important. So I'm just trying to tell you what a cube and a square and all of these things represent. I just want you
Ma'am,
to
on
have an
this,
idea what these things are.
excuse me,
Yes,
ma'am.
yes.
Ma'am, like we do a square and a cube on basic matrices, we know just basic we know. But still, if a question come on reachability and transitive closures, how we are gonna approach?
Okay, if that's what we're trying to transitive closure, we'll just come to that in a second. Give me 1 minute. So that's how you calculate a square, a cube, and a to the power 4. But that's not the only way to do it. This is just a conceptual thing that you should know what a square represents, what a cube represents, what a4 represents. That's what you need to know. At least have a basic idea of it. You don't have to get into the depth of it. And then you can just directly calculate a square. So now we were just doing everything by looking at the previous graphs. To construct a square, we were looking at this thing. If there's one from here, and then there's one here. We're doing all of that here. You don't actually need to do it. You can just simply matrix multiply these two things. You can do matrix multiplication, and then you can get a square. So this a square is basically nothing. This thing that you're representing is nothing. It's just a square. Is a multiplied with itself 2 times, and then a multiplied with itself 3 times, and then 4 times. That's what it is. So instead of doing the longer path, you can just simply multiply these two things, which is easier. So do I need to do the matrix multiplication thing here, or does everyone know how matrix multiplication works?
No, ma'am, don't need.
Let's just do it. Let's just still do it, because so all you do is what you do here is you just simply, for the first one, you just multiply these things, multiply a11 with b11, then add this to this. Okay, if everyone, I'll just discuss this matrix multiplication thing if someone doesn't know about it.
Ma'am, I do not know. If little bit you can tell.
Matrix multiplication, all you do is, let's just say you have a 1, 2, 3, 4, 5, 6, and a 0, 1, 0. This thing here, and then let's just say you have this thing. So for this to be even, for you to even think about multiplying matrices, you would want this thing to happen. So if the first matrix is A m cross n, and then the second matrix that you're trying to multiply should start with an n. So you do know this is the number of rows. You all know about these things, right? The basic number of rows, number of columns things. So this is the number of rows, number of columns, and then you need to have the same number of rows here. The number of rows here and the number of columns here should be same. That's what it is. And then you can have an L here. This is the condition for you to be able to multiply A and B. So if this is A, you need, this is a 3 cross 3 matrix, you need to be a 3 cross something matrix. Let's just take it to be a 3 cross 2 matrix then. So this will be 1, 2, let's just do 1, 2, 2, 3, and 0, 1. So if this is it, what you do is you go by this here, and so you first multiply 1 with 1, then add, this is 1 into 1 plus this multiplication, and then this multiplication. And then you get, so this is your first entry. And when you multiply these two matrices, let's just say you're multiplying A and B, and the order of A is n cross n, this is n cross n. So you'll have a m cross L matrix. The resultant matrix will be m cross L. These two. So this is 3 cross 3, 3 cross 2. So you'll have a 3 cross 2 matrix here. So done with one thing, and then 4 into the next thing you do 1 into 2, then 2 into 3, this with this thing, and then 3 into 1. So you've gotten your 2 columns here, these two, and then you do the same thing with this thing. So it's 4 into, so you keep going on like this thing. First you do this thing with this. So it's simply when you want to have A, B, I, J, what you do is you multiply the ith row here, ith row. So in this case, it's A11, A 11th entry. So you want first column to be done into this. You multiply the entries and then add them. Is this fine now? The matrix multiplication thing.
Yes, ma'am.
Ma'am, then first row it's ma'am second column.
Sorry, what?
Ma'am, then in second line it is from first row with second column.
It is simply if you want A, B, I, J. So I, J means ijth entry. Let's just say it's first, second entry. You want to find the first, second entry of this. First, second entry is this one, right? First, no, it's not this. It's the second, first entry. Let's just find second, first entry. So it's the second row. This is the second row and first column, right? So what you do is you multiply the second row of this one and the second, the first column of this to get this thing. Is this okay?
Yes,
So
ma'am.
you do 4 into 1 plus 5 into 2 plus 6 into 0. And then you write it here. If you have one entry, so what you do is your third row, this is your third row, and your first column. So this is the entry that you're looking for. So what you do is you take the third row here, and then you multiply it with the first column here. It's this. So it's 0 into 1 plus 1 into 2 plus 0 into 0. Is this fine now?
Yes, ma'am.
Yes, ma'am.
This is your matrix multiplication thing. So instead of doing that long method that we were doing, you can just simply multiply these two things. Now, why are we even doing this thing? So we just wanted to do things in this manner to look at this thing because we want to construct this now. So AI, this is the A plus 1, that is matrix, adjacency matrix of transitive closure of G. So this is adjacency matrix of transitive closure of G. How do you construct this matrix? This is basically, so this is the ijth entry. How do you figure out the ijth entry? It's the maximum of AL ij 1 to L strictly less than this. How do you get this thing? What do you mean by this thing? When you do this thing, in this thing, what do you need to, let's just say you have an ij here. So when you have an aij and you have a 1 here, what does this mean? Let's just say that this is a matrix representation, not matrix. This is the adjacency matrix for some graph. What does this thing mean? Can someone tell what this thing means? ijth entry in the adjacency matrix is 1. What does that mean?
There is an edge from I to
L
J.
between I.
Yeah, there's a direct edge from I to J. So if you want to find if there's a direct edge from I to J, then how do we try to find if there is a direct edge from I to J in the transitive closure? of a graph?
The A1 has to have a 1 and not the A2 or A3.
Okay, the simple definition was that if you want there to be an edge from I to J in, say, A plus or in the transitive closure, then you need a path from I to J in A, right? That's how we defined it. So you just need a path from I to J in A. And how do you test for that path? So what you do is, let's just say there's AI and there's AJ. So you test for every path here. So either there's a direct path from here to here. That's A0 for you, right? So sorry, A1 for you. So if there's a direct path, there's a direct edge from AI to AJ, you'll have AIJ as 1, right? Or it's this thing. You have a length 2 path. So in that case, you'll have A square IJ equals 1, right? Or you have this thing. In that case, you'll have this thing as 1. Is this clear to everyone?
Yes, ma'am.
So you just need to figure out if there's an edge from I to J in this thing. For that, you need a path from I to J here. And these are the possible ways, depending on the number of vertices that you have. Let's just say that there were 4 vertices, then you can only go up to A cube, right? You can only have 4 here. You can't have this thing. Something here, then something here, then something. This cannot be possible.
So what's
have,
the maximum number of A raised to N that we can do?
You tell me what can it be? What do you think?
N minus 1?
Yep, it's N minus 1. So the maximum length that you can have is obviously N minus 1. So if there are N vertices, maximum length of a path can be N minus 1.
Excuse me, ma'am, I have a doubt. In the A
Let me
square and
just,
all,
yes,
the diagonal elements will be 0, right, for all the matrices?
yeah.
Okay.
So if you are ever asked to find out if there is like, let's say 2 spaces between AI and AJ, then
Let me just finish this thing first.
Sure.
Otherwise, you won't
Sorry
understand
about that.
what were we discussing here.
Sure,
Why are
ma'am.
we taking a maximum here? You want, so if any of them is true, so let's just say you want to see there's a direct edge from I to J in the transitive closure. So you need to know if there's a path of length 1 from I to J or a path of length 2 or a path of, so you understand the difference between or and right? When you say you want this to be true or this to be true or this to be true, that's what you want, right?
Yes, ma'am.
Yeah.
You don't want them to be they can be simultaneously true, then also this thing will be true, but you don't want them to be simultaneously true for there to be a path from I to J in the original graph. So you want one of them to be true. That's why we've taken a maximum here. Maximum here basically means that if, let's just say they're all zeros, let's just say this is also 0, this is also 0, this is also 0. That means that there's no direct edge, then there's no 1 length path, no 2 length path, no 2 length path, and then no 3 length path. So you don't have a path at all from I to J. That's what this thing means, right? If you've tested everything, that this means there's no path from I to J. So you'll get a 0, 0, 0, and a maximum of it will be 0. So you'll get a 0 here. But if there's, say, 1 here, a 0 here, a 0 here, then you'll have 1, 0, 0, and the maximum will be 1. So even if there is one way to do it, one way to go from I to J, either directly or via an edge or via 2 edges, then it will be considered to be 1, right? So you'll have the maximum to be 1 here. This will just give you that this would just mean that there is a path from I to J. You just want to make sure that there's a path from I to J. So when you do this thing, AL thing, you're just checking for ways for it. So if there's a path, a direct path or 2-edge path or 3-edge path, that's what you're looking for. Is this part clear to everyone? Why we're taking a maximum of these things here?
Yes.
This is how you define the transitive closure, the matrix for the transitive closure. Even if you don't understand this, learn this thing. Otherwise, they've already explained why we're doing this maximum thing here. And then you go in the depth of these things. So, okay, let's just not go there. That's all. That's how you calculate the transitive, the matrix, adjacency matrix of the transitive thing.
Ma'am,
Yes,
hello.
yes, yes.
And this A1, A square, A3, when to put 0, when to put 1, that I understood. With diagram also you have shown. But this 1, 2, and 3, that index, what does it actually mean? That 1, 2, 3, that A1, A2, A3, that exponent, what 2, what does it
This,
actually mean?
okay, this means this thing. When you say a square ij and this is 0, this means that there is no path that this cannot happen. So you cannot have ai to ak and then ak to aj. That's what, if there's a 0, this cannot happen. If there is a 1, that means there is some ak such that there is an edge from ai to ak and then there's an edge from ak to aj. And then for this one you have, so if you have a 0 here, that means you cannot have this thing. You cannot have AK and AN such that AI is going to AK, then AK is going to AN, then AL is going to AJ. This is not going to happen if you have a 0 here. But if you have a 1 here, you will have this thing. You will see this thing in the graph.
Okay.
For
Thank you,
some
ma'am.
AK and AN.
And this last point that you have written, n vertices, n minus 1 max length, that point could be explained. Actually, I was disconnected that time.
This is nothing if you have n vertices in a graph. Maximum length
Maximum
that
length
you can
is
have. We were discussing this thing. So maximum length of any path can be n minus 1 only. So if you have n vertices, say you have 4 vertices, so you cannot have a path of more than 3, a path with length more than 3. So this is 1, 2, and 3. So the length of it is 3. You cannot have something with length 4 or length 5, so completely not possible, not even 4. So you'll have n minus 1 as maximum length of any path if the graph has n vertices in it.
Okay, thank you. Means any graph with n vertices, the maximum length of the path possible is n minus 1.
It's the maximum length. And
And last query, the condition of this matrix, that I understood, but when we have to create that matrix, we have to do it by manually hit and trial, or there is some process or priority that, like suppose we have to create a square I comma j, that condition
you
I
just
understood.
multiply it. That's, you don't do all that. The things that we did initially, you don't do that. You just simply multiply the matrix. So if you want to find a square, just multiply a 2 times, and you'll get a square.
Okay.
And that's the same thing as the a square we discussed in the beginning.
Okay.
This still represents the same if there is a path of length 2 from ai to aj
Okay.
or not. That's the same thing.
Means a square, when we have to find out the exactly the a into a matrix multiplication.
What?
And then means when we have to do the a square matrix, we will do the exact matrix multiplication of a cross a, right?
Yes, you'll do the exact matrix multiplication. But one thing you keep in mind is when you multiply these things, so your during multiplying your 0, 0, 0 into 0 is considered 0. I'm telling you how you should multiply it. 0 into 1 is considered 0. Multiplication thing is as usual that you do, because you need to multiply things and add things while matrix multiplication. But your 0 plus 0 is going to be 0. 0 plus 1 is going to be 1. 1 plus 0 is also 1. Your 1 plus 1 will be considered 1 only. Because why this is considered 1 is, you just have to, when you do aij, so you just need to, this 1 represents true. True as in what sense? That there is an edge from I to j. That's what it represents, right? So 2 means nothing. 0 means there's no edge. 1 means there is something. 2 means there's nothing, right?
Okay.
So you keep a 1 here. You don't go above 1. So either there's a 0 or a 1. That's how you multiply and add things in matrix multiplication while you do these things.
Okay, thank you.
Ma'am, if we want to find a cube, then we can also do it by matrix multiplication.
You will have to do it by matrix multiplication. Otherwise, you can't just keep doing this long process that we discussed initially, right? The one that we discussed here, that there's a path from here to here, here to here. It's very tedious.
Yes, ma'am.
It take a lot of time. So you will have to do matrix multiplication only. These are the rules that you have to follow while multiplying things. Because the entry, you have to make sure the entries are only 0 and 1. So you can't have a 2 here.
So A cubed would be A square into A, right?
Yes, it's A square into A.
1 into 1 is 0 or 1?
Here we have to
It's
consider
1, 1. The matrix multiplication is the usual one. This is the multiplication basically represents an AND. So it's like 1 and 1. So if you have a 1 and 1, you will get 1. And this represents OR. Even if you have a 1 in one of these, you still get a 1 here. That's Boolean algebra. You don't have to get into that. You just have to remember these things. Let's not complicate the things. Let's just stick to this thing. While multiplying the matrices, you'll have to do this thing. Is this okay? So whenever you see a 1 plus 1 or something, don't write 2 there. Don't write anything else. It can either, it's the entries are either 1 or 0. You can't choose anything else. Even if you get something, you will get these things. That's the algebra that you have to follow. Okay, moving on.
Just a question. When we need to find A cube, we need to do A square into A or A into A square, because in matrix multiplication, those do not always give the same answer.
No, they always do give the same answer. A square into A and A into A square is the same thing. They don't give the same answer when you have different matrices.
In this case, they will give the same answer.
Yeah. When you have the same base, that A is same, you get the same thing. This is the same as this thing.
Okay, okay. Thank you. Sorry.
So then if you have to conclude this, okay, that's enough for you to know if there is an edge. We will discuss what all of these powers represent, and we'll discuss the shorter way to calculate things. That's just matrix multiplication. And then we'll discuss an important algorithm, which is, okay, so first we'll discuss the reason to discuss this algorithm. So let's just say you have a graph. Let's make the graph first. Let's say you have this thing.
Ma'am, can you explain what is planar graph?
Okay, so planar graph is when you have, let's just say you have these, this is a graph. So you just need to make sure that it lies in the plane while you connect the edges. So what does that mean is that two edges should not be crossing each other. So you can have this thing, you don't need to have this thing. You can do this thing, right? You can do this thing too. But then you can't connect these two, because if you connect these two, you'll be crossing this edge. So the edges should not be crossing each other. That's all. That's what a planar graph is. When you're drawing in the plane, your edges should not be crossing each other.
What is acyclic graph?
We've discussed all of this in the last class, the last summary session. We'll discuss that here. We won't be able to do the summary for week 11. It's in the last summary session for week 11, week 10. Acyclic is basically where the graph doesn't have any cycles. There's this thing. Let's just say this is 10. This is a firstly, this is a weighted graph. You must not have seen this thing before.
Ma'am, I have doubt in some questions. Can I show
No,
from camera? If you can.
We're not doing the questions right now because there's a lot of summary left for week 11. So we'll do that now.
Ma'am, then when we'll do the questions?
You can do that in the doubt class. You have a doubt class the day after tomorrow. So this is your weighted graph. Weighted graph just means that there is, let's just say that these are airports and this is the cost to go from this airport to this. That's what weighted means. So initially when we used to discuss this airport thing, we just We just used to talk about if there is a path from 0 to 1, from airport 0 to airport 1 or not. That's so an edge just represents that there is a path from 0 to 1, and this represents some cost to it. This is basically that there's, let's just say, the fare to go from 0 to 10, or the ticket prices are like 10 something. So that's what your weighted graph means. This is a weighted graph. And then you need to find the shortest. Let's just say that this is the time taken. Let's just say that you have something burning here, and then this is the time taken to reach the fire from here, to reach the sparks from here to here. This is 10, let's just say this is 10 minutes, this is 20 minutes from here to here, and this is 80 minutes from here to here, 70 from here to here. That's what your weighted graph is. You can associate any weights to it. Weights are generally mentioned. What are the weights representing here? And then you need to find the shortest path from single source. So source is the thing that you start the thing with. So source could be 0 or 1. Let's just take the source to be 0 here. Source means that your fire started. Let's just say that your fire started from here. You call 0 to be the source. And then you want to find when are the vertices going to burn. So at what time are each of these going to burn? We need to find the exact time for all of these. So how do we do this? The first method that we can use is Dijkstra's method, which is this. This is Dijkstra's algorithm. How do you? So I hope you know why we're doing the Dijkstra's algorithm. It is to find the time taken for each of the vertices to burn, right? The minimum time, the time taken for them to burn. If the fire starts from here, then what's the time taken for all of them to burn? And we'll do for each of the vertices. So how do you do that? First, you start from 0 and you consider that to be the source vertex. And then I'll just directly give you the algorithm for it. First, you mark all the vertices here. And you make a table for it. Table in the sense, so you started from 0. 0 is first marked as 0. So you mark this 0 and all the other vertices infinity. Infinity basically represents that this thing is not reachable yet. So when you put a 0 means that this is reachable. The fire has started here, and the other things are infinity for now. They are not reachable yet. And when this thing burns, let's just say that this thing is burned. So I'm putting a tick when a vertex is burned. So this thing is burned. Then the fire can catch up to this point and this point. So these two are directly connected. Other parts are not directly connected. So that it's going to catch up to here and this point. Then you update these things. So from here to here, you will take
Means it is
10
reachable
minutes.
to every point.
Sorry, what?
Ma'am, infinity means it is reachable to every point.
Infinity means that you are not in touch with. You don't need to know this thing. You just need to start at the. So you just need to know that the starting point, the source of it has 0 initially, and all of the others have infinity, because they're not reachable yet. It's, let's just say that the fire started from here, so only this thing is reachable now, and all of them are not reachable. So they'll be reachable when this thing gets burned. Is this all right? Or in simple words, you can just remember the source vertex initially has 0, all the others have infinity. And then when this thing is burned, you try to start looking at this. And this thing is not even important. This step is not even important. The other steps. So when you go here, you see that it takes 10 minutes here, so you write a 10 here. Then from this is also directly connected to it, so you write a 20. And all the other vertices that are not directly connected to it still are considered to be at distance infinity.
Ma'am,
Because
shouldn't you write a
they
10
can't be
against
reached.
1 and not against 0?
Yeah, this just gets, this is, the source always remains 0. This is 0 that you assign to it. Don't get confused with this thing. This is the vertex number 0, V0, and this is the 0 thing that you have. 0 means 0 time to burn. Because you don't need any time for this. This gets burned at time 0. You don't need any time for this to burn. And then you have a 10 here and an 80 here. Because This is you just take the direct edges, the ones that are directly connected to this vertex. So this is directly connected and this is directly connected. So put a 10 here and 80 here, and put everything else to be infinite. And you just write down the vertex that is already burned. So 0 is already burned. You have picked it and just write it here so that you know that it is already burned. This is for you to know that this is burned and the time is 0. And then you take the minimum of all of these. So the minimum of all of these is 10. So you mark this vertex B1 and then you put it here. So we'll go to 1 first. Why are we taking this one first? Because this will get burnt first and the fire will start going from here to here in every direction. So while this is burned, this is still in the process. So you're only here something. The fire has only reached till this point or something. So this thing is still in the process. Is this part clear? That's why we take the minimum thing here. And then we just consider this vertex to be burned. So we consider this vertex to be burned first because this will burn at time t equals 10 and this will burn at time t equals 80. This is burned first and then we lock this thing up here. So this is fixed now. You don't change this thing. So this distance or this time has been fixed now. This weight is fixed. 0 is already fixed and then you see where you can reach from 1. So you take 60 there and 20 there. But you already know that the distance till 1 is 10. The time is 10. So it's 10 and then you add a 60 here for 4.
So every
So what you're
vertex will
doing
be
here is,
fixed, right?
okay, but let me just complete first and then you can ask doubts. Let me just complete this thing first. So what you do here is, before moving on to the table, I just want to do it just first you start with 0, the fire's here, then it reaches here in 10 minutes. So 1 is burned. So 0 was burned at time 0, and then at time t equals to 10, your 1 gets burned. This gets burned. So you just put a tick here. I'll put a tick whenever a vertex is burned. So this is fixed now. The time for this is what we're trying to find is the time at which the vertices will get burned. So this is going to get burned at 10. All right. Then we move on to this and the directly connected vertices from 1. So the directly connected vertices from 1 are 2 and 4. And the others are still at infinity. So this will be considered infinity. This will be considered, not this one, infinity and infinity. These will be considered infinity. And these will be considered a distance of 60. But the total time taken is 10 from here and 60 from here. So the total time is, for this vertex, it's 70. For this one, it's 70. And for this vertex, it's 10 plus 20, it's 30 here. So for this vertex, it's 20, this vertex, it's 70. And then you move on to the next ones that are connected. So you again pick the shortest time because so this one is the smaller time. So you pick the 31. And then you move on in this direction. So 30 plus 70 is going to be 100. So this is going to take 100 time 100. Means this will take 100 minutes to burn. This will take 70 minutes to burn. And then you move on to this one. So you'll have 70 plus 50. So this is which ones are burned. This was burned. Then the minimum distance, the minimum time was this. So this is also burned. So you burned the one with the minimum time. This one had the minimum time at first. This got burned. Then you look at 2 and 4. So 4 has time 70, 2 has time 30. So this will get burned first. 30. The second one gets burned first. And then you move on to the next ones. So the directly connected ones to 2. So this has only one edge to it. So this will get burnt next or whatever. This will get burnt at time 100. So this is burnt as well. Then you look at this thing. At time 100, this is burnt. This is burnt at time 30. And this is burnt at time 20. This was burnt at 0. So all these 4 vertices are covered. We're not sure about. So then we move because it does not have any other edge. So it is going to burn at 70 only. So this is 10. And then you directly go to this one. So after getting done with the minimum time one, you come to this one. So this is 70. And then this gets burned at time 70. And then the fire starts from here. So this will get burnt at 120. If you go this way, it will get burnt at 120. And this thing will get burnt at 70 and 15, 85. But then you see that there is another edge from here to here. So you add 30 there. Just give me a minute.
Ma'am, it burned the minimum age first.
Yes. But
So,
that's how it happens, right?
ma'am, after
There's a fire.
6 will burn.
Sorry, what?
Ma'am, after 6 will burn first.
We're not writing the order. We're just writing the time at which the vertices get burned. That's what we want. As in this example, this gets burns at 10, this gets burned at time 30, then this one at 100, then this one at 70. So we just want the time for it. So if you will go from this way to this way, this is now already burnt, right? This one is also burnt. Then you have these two remaining. So this will burn at 85. So this get burns after this one because this has the minimum distance, right? The minimum time is this. So this is
I'm
going to
really
burn.
sorry for
And then,
interrupting, but
yes,
is it possible to fill in this table while we are doing this? Because I think I don't know.
I just
I find it
wanted
a little.
to do it this way, and then we'll obviously go to the table because
Okay.
that's the algorithm for it.
Okay,
And
ma'am.
then you go from here to here. So this one is 70 and 15. This burns at 85. And
Very
then this
sorry, ma'am,
burns
just a
even at,
query.
let me just get done with this thing first. 85 and 30 is 115. So if you go from here to here, this will get burnt at 115, and this will, from this path, will get burnt at 120. So you'll obviously take this path. So this is going to be burnt at 150. This is what we're doing. Now this is the algorithm for it to do it this way.
Ma'am,
Let's
can you
just
please explain the 5th part again, how it is 115? The last one.
if you will take this route, you will reach at 120 time. So at 120 minutes from the start, t equals to 0 started from here at time 120. This, if you will take this way, it will burn at 120. If you take this path, it will get burnt at 150. So obviously it's going to get burnt first from here, right? The
Okay.
time for this vertex to burn is 150, not 120, because it will get burned first from here. Now we look at the table. So you have 0 here. So what you do is you just take the minimum distance. The minimum distance is here, and then you burn this vertex 1, and you write the burned vertex above, just to make sure that this vertex is done. This vertex is burned. And then you write a 0 here. So this doesn't change because this is burned at time t equals to 0. This is burned at time t equals to 10. So this is the fixed time now. You don't change this thing. Now these things will change. Now when you look at this thing, so you have a 20 here and a 70, a 60 here, right? So 10 is what takes you to reach 1, and then you'll add a 60 to it. So let's just go to the third one first. So to reach the second one, this is 10 and this is 20. So you write a 30 here. Because this is, if what you do here is, previously it was 80. If you get anything lesser than that, you update this thing. Once burned, you can't update things, but now you can, because vertex 2 is not burned yet. So you can update things. So from this way you had 80. From here you have 30. One is burned. So
I didn't get it. Can you please explain this again? The
okay, I
table
think
of
it's getting
1.
a little confusing.
Yes, ma'am.
What we do is we start from V0, right? And then we see that the directly connected edges are V2 and V1. And the one with minimum distance is this one, V1, right? So this gets burned. This gets burned first, right? And then you fix the time t equals to 10. So this gets burnt at 10 equals to 10. You don't change this thing now. 10 is not going to change in the upcoming changes that you're going to make to this table. Then you go to this thing. Then you go to vertex 1. And then you look at its neighbors, its direct neighbors. So it's V4 and V2. And then you look for the minimum time. So from till V4, you have 10 plus 60, so it's 70 there. Right? And from here, you have 10 plus 20, so it's 30 here. So it's 30 here. And 0, 10, 30, and the third one is still at infinity. So the ones that are not directly connected, so V4 and V2 are directly connected, so you're going to update these things. And the ones that are not directly connected to it, like this one, V3 is not directly connected to V1, so you put an infinity here. V5 is not directly connected to V1, so you put an infinity here. V4 is directly connected to V1. So you don't put an infinity, you put a 10, the one fixed for this one, and then a 60 for this. So you get a 70 here. Is this much fine? And this is also at infinity. Is this fine to everyone?
Ma'am, V1 is 10 and from V2 it is 20. So 10 more is needed. So that's why you write 10 here.
Here?
Yes, ma'am.
This is the time that you require for this to burn. But it is now fixed. I am putting a box here if it is fixed. So this was fixed here because it gets burnt at 0. And this is fixed here because there's no, if you see the minimum one, this is 10, let's just say 10 minutes from here, this is 80 minutes from here. So this is the minimum one. So the minimum gets burned. Now this is burnt. This is burnt at time t equals to 10. You don't change it now. So in the upcoming things that we'll write here, 0 is going to remain same. 10 is also going to remain same. They're not going to change.
And
This
ma'am,
is already burnt.
how 30? Can you please explain this also?
You go from here to here. So this is already 10. This got burnt at time equals to 10, right? Now your time is 10. Then you're exploring this thing. So it has only two direct vertices. Everything else is at infinity. So from here, this is at infinity, this is also at infinity, this is also at infinity. This is at 60, but it already has a time 10. The time will be 70, right? So we put a 70 here. This is already a time t. For this to burn, you will take time 10, which took you to burn this, and then 20. So you will get the total time will be 30 for this to burn. So you write a 30 here. Is that okay?
Okay, ma'am.
You just add the previous one, the one that you fixed, no, you add that to the other distances. So this one you fixed at time t equals to 10. So you add 10 to 60 and 10 to 20, the fixed one. Okay.
Okay, ma'am.
Then you look at the minimum here. So you don't, this is already fixed. So you don't consider this to be the minimum. This time you'll only check for the minimum among these two or these four because this is already fixed. So you just need to know this gets burnt at 30 and this gets burnt at 70. So this will get burnt first. So this is the next one. So you'll put a 2 here. And then this is fixed. Once you fix these things, this gets fixed. So this is 30. This gets fixed and this gets fixed as well, right? And then you look at the third vertex, but third vertex doesn't have anything connected to it. So nothing gets changed. From third vertex, nothing gets changed. And then you look at this fourth vertex. Fourth vertex is 70. From 70, you'll have 70 plus 50. So it will be 120. So fifth vertex will be at a distance 120. And from here, you get 70 plus 15. So your sixth vertex will be at 85. And fourth vertex is at 70. Is this all right? Is this okay to everyone?
I have a doubt here. Like we have two things. One is the straight path that travels from 0 to 5, which is a linear path. Whereas when you talk about 2 and it's again a parallel path which has a diagonally connected thing. So the travel of the fire, let's say that the fire starts at 0 and it reaches 5. You said it's 120, but when it goes, it travels through 6, then it is 115. Did I understand right?
Yeah, that's how it
Okay.
works.
Okay, so when it comes for fire, I mean, I do see understand the part of the weight edges weights here. So when we talk about this thing, so we don't have to think about anything in parallel. What will happen to 2 or 3 when we are talking about 5, 4 from when we start from 0, 1, and 4 and 5? Is it?
I don't think I understand your question.
No,
No,
when
this is your okay. What's your question?
no, my understanding is like if we talk about from the travel, I mean the movement of the fire from 0 to 5, that's the thing. So we start doing it. So in that case, even though we talk about 0, 1, 2, and 4, and 6 and 5, so we don't have to worry about 2 and 3 in that during the time.
Yeah, because you don't have a path from here to here, right? And it's you're burning these things. 0 is burned, 1 is burned, 2 is already burned. Now why do you worry about 1 and 2? You don't have to worry about these two because they're already burned. And then 3 gets burned after it because or even if it's not burned after it, let's just 3 doesn't have any consequent edges to it. So 3 is not a problem here. Okay, let's just continue with the algorithm first. So you have, this is already burned, this is already burned. So you have these three things. Now you pick the minimum out of these things. So 70 is the minimum. So the fourth vertex gets burnt next. This is going to get burnt next. So you pick the 70 here and put a 4 here. This just tells you which one is going to burn. And then you put a 70 here because it's now fixed. And then from 70 you will move forward. So 70, now you have V5 and V6. The directly connected ones are V5 and V6. So till this vertex is 70 plus, so you just add things to this. The distance from here to here is 50. You add 70 to 150. 50, and you get a 120 here. You don't have to, this was still infinity, by the way. These two, when you were checking from V2. So from V2, your V5 and V6 both are at infinity. So you put these things at infinity. V2, you have a 10. These were already fixed, right? The 31 and all of these are fixed. Then V4 is at a distance of 70. Yeah. And then here you change the things. So you add 50 to 70. You'll get a. So the time here was this got burned at time 70. So this is going to burn at 70 plus 50.
Ma'am,
120. And this is
ma'am,
just 1 minute. Give me 1 minute. And this is going to burn at 70 plus 15, 85. So you're going to have an 85. And then obviously this is the minimum. So this gets burned first, and this gets fixed. So now you choose the minimum out of these two, and the minimum out of these two is 86. The next one going to burn is the fifth one. So the fifth one burns next.
excuse me, ma'am.
Just give me 1 minute. 0, 10, 30 are already fixed. Yes. What were you saying?
Ma'am, I'm asking that in fourth, means in the fourth column, in the fifth, we take 120 or 115?
We'll update it. Don't worry. Here you will take 120 only because this is 70, this is 50. So if you will go via this path, you will get 70 plus 50, 120. So via this path, it's 120 only. And this one is 85. But in this one, we'll update it. This is not
Okay, ma'am.
burnt yet, right? You can't update the ones that are burned. You can't update this one, because these all are burned. You can't update 0th, first, second, fourth vertex after this stage. Fifth vertex can still be updated.
Okay,
Sixth
ma'am.
vertex can also be updated. So the next one to burn is this one, because this is the minimum time now. So this will get fixed 85. The one that gets burned, the one that you write here, fixes itself. So now you don't change this. These were already fixed, and then you just have 120. So what from 85, what you do is if you get a better time than this, you'll update it as 115. So this is in this whole example, this had happened only once, that you have to update this thing to this thing. Otherwise, we were going in a pretty straightforward manner. So you update this thing here if the time that you get from this thing. The fifth is the bond. Then you look at fifth. Fifth is this one. We've written the wrong thing here. Six gets burned first. So 6 you write here, and then you focus at 6. And 6 has a direct edge with 5. So you can update this thing because it's directly connected to 5. If you get a lesser time, you update it as 150. If this were 130, you'll keep it as 120. Is this all right? Is this table clear to everyone?
Yes.
Yes, ma'am.
Any doubts so far in this table, how you construct this thing?
Ma'am,
These
just
are the
last,
vertices that gets burned. Yes.
ma'am, just last one, 4, 5, 6. Can you just explain how did we decide here?
Yes. When you have the fourth one is here, right? We have 70 here. So it's in the process here. Now you write the fourth one because these are already the burnt ones. 0, 1, 2, 0, 1, 2. These three have already burned. So you'll focus on this. Out of all these three distances, the minimum one is 70. So this gets burnt next. Fourth vertex gets burnt next. You write it here. And then these are the fixed times. They don't change because they are already burned. 0, 1, 2 are already burned. 4 is already burned. So you don't change the time of these. And then you update these 2 times. So what you do is, if you are at vertex 4, you just see whatever is connected to vertex 4. So V5 is connected, V6 is connected. This is at 15. This is at V6. V6 is at 15 and this is at 50. This is it. So what you do here is, and the time here was 70. So if you will go here, the time will be, so to vertex 6, it is 85. You write in 85. 70 plus 15, 85 time you get at vertex 6. And then here, 70 plus 50, you get 120. So you write a 120 here. Is this part clear? How you do this thing?
Yes, ma'am.
Okay. Then you look at the minimum of these two because these are already burned, and the ones that are burned, we don't look at the minimum of those. So we just look at the minimum of the ones that are not burned yet. So these two are not burned. So the time here is 85. This is 120. That means this is going to get burned first. So we write a 6 here. These times are already fixed because they are all burnt vertices. So they are not going to change. This is also burned. So this is not going to change. And then you can have a better option for this one. So from V6, you see that there's a path from, let's just say if there was no path from V6 to V5, then this will be 120. You don't have to see anything. You don't have to check for anything, right? Because
Yes.
there's no path from V6 to V5. But if there is a path from here to here, what you do is, and the time is coming out to be 115 from here. But previously it was 120. So how you update time is, if there is a lesser time, then you update it. Otherwise, you keep it the same. So if it's 115, you update it. If it was 130, you won't update it. You will keep it
Yes,
as
ma'am.
120. All right.
Yes, ma'am.
And you only change the ones that are directly connected to it. Like you keep infinity everywhere else. So if these two are directly connected to it, so these are already fixed. These two are directly connected, so you update these. And if there was some other vertex which was not, let's just say there was V7 which is not directly connected to V4, then in the seventh one you have an infinity here. Is that all right? If it was infinity from start, it will remain infinity here. Is that okay? So you only update the things, other things you keep infinity. The ones that are not directly connected to it are kept at infinity. Is this part clear to everyone?
Yes, ma'am.
Okay.
Yes, ma'am.
This is your Dijkstra's algorithm. And then it works for undirected graphs as well. So even if you have an undirected graph, this works just as it is. And then there are some important things that you need to know about when to use the Dijkstra's algorithm. So when your weights are all positive, then only you can, at least non-negative. So if your weights are all non-negative, then only you can use Dijkstra.
Well,
Otherwise,
so
you
what is
can't
the
use.
so in that case, what is the difference between then undirected and directed graph?
Is there a doubt? I can't hear you.
Ma'am,
Okay.
what's then the difference between directed and indirected graph in Dijkstra's algorithm, ma'am?
There's no difference. If you'll have it, even if you don't have these things here, you know that if this got burned first, then this is going to get burned. And if you get an undirected graph, what you do is, let's just say these two vertices are there, you take it to be this thing. So you consider that there's an edge from here to here. So if there is an edge from here to here, and this is undirected, so you consider an edge from here to here and here to here too. That's how you consider it. Is it fine? So if you get an undirected graph, you'll consider that there is an edge from here to here and here to here. So if you see something like this thing,
So
let's just say
in
you
that
have,
case, 0 to 1, it is 20.
no, it's not 20. We're just saying that if you have an undirected graph in this case, what you do is, let's just say you have this. Then we consider it to be from here to here and here to here as well. That means you can go. That means you can go from here to here and here to here as well. So in this context, it will mean that you can go from here to here and here to here as well. But this is the source. The fire started from here. So if you're going from here to here, you wouldn't need this thing, right? Because it's already burnt. So you wouldn't need this thing. This would mean that there's a path from here to here and here to here as well. So that means you can go from 80 to 20. So this will burn at. That's not going to change anything. I can't. We don't have enough time for me to explain all of it. But this is not the directed thing. Is not going to change anything at all. You just have to.
Ma'am, for
You just have to
undirected,
know this one
same
thing that
as
it's.
that of directed. Because
Sorry, what?
ma'am, for undirected, it is same that as of directed.
Yes, it's the same. That's what I'm saying.
Because one path is already burned, how could I go
Yeah,
to
you
it?
can't go the other way. That's why I'm not getting into the algorithm. So if this one's already burned, you can't go from here to, even if there was a path here, this one is the shorter one. So while doing the Dijkstra algorithm, what you do is you choose the shorter one between these two. So if this is already more than this one, then why would you go this way? You burn this because this was lesser, right? That's how we burn things. That's what we do here. We get this burned first because this was lesser than 30. So if you have a path from here to here, why would you even go via this path? So the directive thing is not, all in all, it's not going to change anything. You can just go from here to here. That's what it means. That's it. So in a Dijkstra algorithm, your weights are positive. Is there a
Yeah.
doubt?
So the Dijkstra algorithm always comes with the weighted one. It cannot be without the weights.
Yeah, you need a weighted graph to perform. Dijkstra algorithm is to know the minimum, the shortest path from a single source. So if this is the source, you want to know it's the minimum distance or the minimum whatever the cost from here to every other point. That's why you perform Dijkstra algorithm.
Okay.
So if you don't have weights here, what are you even looking for then? Dijkstra needs weights, and weights need to be positive. Why can't you have negative weights here? Because if say you have a negative weight here, then what happens is, so in Dijkstra algorithm, what you do is you go from here to here, and then let's just say you go from here to here. So what you do is, the basic thing that you do in Dijkstra is, if this is 30, this is 50, and let's just say this is minus 30. So what you do is you look at this is, if this is the source vertex, you look at 30, then you look at 50, and then you say that, and then you burn this immediately. So you mark this as tick, that this is done at time t equal to 30. So this is now fixed and you can't update this thing. That's the major feature of Dijkstra algorithm, that you can't change it after it is fixed, right? That's what we were saying. The blocks that we fixed here, we can't change them in the next. So if this gets burnt, you can't change it from any other path. But if you go via this path, you'll get a 20 here. You're getting a better time here. That's why you can't use Dijkstra algorithm with negative weights. Is this all right? So when you have a negative weight, don't use Dijkstra algorithm.
Can you repeat this?
When you have, let's just say these are three, this is the source vertex, let's just say,
Okay.
and you go from here to here. So in the major feature of Dijkstra algorithm is that once you find the minimum one, so if this is the minimum one, that's what you do, right? You write 30 in the table, then you write 50, and then you choose the minimum one, and then you burn it. And then you write the vertex step. Let's just say that this was second vertex, so you write V2 here. That V2 is burned. Now, if it is burnt, you can't update. And what do you do in the coming iterations? You can't change this thing. Now, the time is fixed. You can't update this time later. That's why I'm repeating. This is something that's repeated a lot of times. You can't change this. Once it's burned, you can't change this thing. And the minimum one gets burned. So you'll burn this because it has the minimum time. And you can't update it later. But you can find a better time from here. If you go from this path, you'll find 50 minus 30. This is not for time. I'm just giving you an example. So you can get a better weight here, the lesser weight here, which is 20. So if you would have gone this way, you would have found the better way. But you can't do that in Dijkstra algorithm. That's why Dijkstra algorithm doesn't work for negative weighted graphs. Is that all right?
Yeah, thank you.
Because you can always find a better approximation from some other way if there's a negative edge included.
Is the popular problem of Manhattan problem is associated with Dijkstra algorithm?
What?
the Manhattan problem is associated with Dijkstra?
I'm not sure which problem it is.
Okay, thank you.
I don't think that. Okay. Then next up you have. So what do we do? And the next thing that you have is one important feature that I want you to remember. The main points about Dijkstra is once you find the minimum weight, so you put one thing that you first thing is that you put everything at infinity that doesn't have a direct edge with the given vertex. So if you don't have a direct edge with zero, you put everything else at this thing, third, fourth, fifth, sixth vertex will be at infinity because they don't have a direct edge with this. So that's one thing where to put an infinity and where to put a number. And then the one with the minimum, the directly connected one with the minimum time is going to get burned first. So this gets burned, and then you can't change the time of the one that you've already burned. So if you burn this thing, this one, this has the minimum weight here. So this gets burnt, and now you can't change it afterwards. It remains constant in every iteration. So these are the two main features of it. And then we have, so what do we do when we have negative weights? How do we deal with negative weights then? So for negative weights, with, okay, let's just talk about negative, we'll talk about negative cycles later. We use Bellman-Ford algorithm. So how does this algorithm work? In Bellman-Ford algorithm, what we do is let's just take the same graph. This one, right? Let's just say you have 0, 1, or let me just take a smaller graph because this is a very long method. Let's just say you have this graph. Then in a Bellman-Ford algorithm, what you do is, let's just say that there's a weight 2 here, 3 here, 4 here, a minus 10 here, and a 5 here. Let's just say you have these things. So it's better to use Bellman-Ford when you see something negative. That doesn't mean that for a negative thing, it usually doesn't work. That's okay. Let's just forget the thing. Always use Bellman-Ford for negative weights. So when you have this thing, you first write down all the edges here. So you write down there's an edge from 0 to 1, then from 1 to 0 to 2, then from 1 to 2, 1 to 4, and then 4 to 5. These are all the edges. You collect all the edges first, and then you draw the table again. So this table is different from what we did earlier. So
Excuse me,
you
ma'am.
don't actually need a table for this one. Yes.
Ma'am, what does this minus 10 actually represent?
Okay, it just represents in sometimes what happens is there can be things negative. In cost, you cannot have negative things. Or let's just say, so the one that we did, the burning one, the time can't be negative, so we can't take it in that context. But there can be other cases where you might have something like you it can represent as, like, let's just say that you lose 4 rupees somewhere. So let's just say plus 4 represents the amount that you lose, and minus 10 represents the amount that you gain. So let's just consider it to be this thing. So if you go via this route, you lose 3 rupees. And then if you go via this one, you lose 4. Via this one, you lose 2. Via this one, you gain 10 rupees. And then via this one, you gain. So you just need to find out which ways should you go through. So this can be one thing to look at. This is how you can practically do it. Is it all right?
Okay, ma'am.
Okay. So you have this thing then, the Bellman-Ford algorithm. So what you do is, let's just say, First, we count the number of edges. There are five
So,
number of.
so ma'am, this is the alternative of Dijkstra algorithm, isn't it?
That's what we said. When the weights are negative, you use this thing. And when your weights are positive, unless it's not mentioned to use Bellman-Ford algorithm, don't use this one because it's a long algorithm. Dijkstra, in case of positive weights, you can use both of them, but this is a longer method, so don't use this one. Dijkstra is easier for positive weights. If you see a negative weight, then use Bellman-Ford algorithm.
Ma'am, what are you saying here? Plus 4 lose and minus 10 gain. Actually, I lose my network at that time.
Okay, there's an example of a, let's just say, a cab driver or someone who's, these are the paths, let's just say these are the places and then these are the paths there. So if he's going this way, if he's on this route, he'll he'll have to pay for petrol and everything, right? Because he's still losing money. If he's looking for customers and he doesn't find any customers there, then he lose 3 rupees there, let's say, lose 4 rupees on this path, lose two on this path, and then he'll find a passenger here, so he'll gain money here. That was the example that I was talking about.
Okay, ma'am.
Okay. Then you have number. So first you write down the number of edges. There are 5 number of edges. So you perform this thing 4 times. So if you have n number of edges, you perform what you perform n minus 1 iterations of what you're going to do. N minus 1 iterations, where n is the number of edges. In this case, you will perform 4 iterations. 4 iterations. How do you do that? So you start off from here, and you will see 0 to 1. Just write these edges as this, or let's just do it directly here. So if you'll hear, this is a distance 2. This is a distance 3. You can directly do the things here, and then this is at infinity. This is at infinity, and then you don't have to put an infinity here. Just give me 1 minute. Let's just keep the same graph to make things better, because then you can compare the two things, right? Let's just do the same graph again. Let's just have you say you have this thing. So number of edges are 1, 2, 3, 4. So first you mention all the edges here. Where edges are 0, 1, 0, 2. It's just take the list of the edges here. That's all. That's what you have to do. 1, 2, then 1, 4, 2, 3, 4, 5, 4, 6, and 5, 6. Just do all the edges here.
Uh, does it also mean the direction is from 5 to 6, or does it mean like uh,
this one just means that it's 6. It's the directed one, right? In undirected graph, you mean that it's both from 5 to 6 and 6 to 5. This one is directed.
oh, then it should be
It's
6 to
from
5,
6 to
no,
5,
ma'am?
not from 5 to 6. So we have a 5, 6 here.
Okay, the direction seems to be from 6 to 5. That's right.
Are there people in the meeting? We're continuing with this session.
Yes.
Yes, ma'am.
Yeah, ma'am.
Okay. So we're talking about this thing. So at
We
one you have a
lost you
10.
for a short while.
Yeah, I just got disconnected. And you write all the similarly, you write all the vertices, all the edges. And then what you do is, so at one you see, so this is an edge and you find the distance here and you write 10 here. So it's 10 at one. What you want to do is you initially write it, so you write a 10 here because it's a 10 here. Then from 0 to 2, it's here. Then from here you have 10 plus 20, so you get a better thing here. What you do is you use these edges. So you're only, how do you can't be doing everything here because there are a lot of edges. So you just use the edges that are there. So 0, 1 at this edge gives you 10 at 1. So you get a 10 at 1. And then 0, 2 gives you 80 at 2. You write down 80 here. And then you look at 1, 2 edge. 1, 2 edge gives you this one 10 and this one 20. So it gives you a better approximation. So you get a 30 here. So initially it was 80, now it's 30. If you get a better, if you get something better, then you update it. Otherwise, you keep it as. So if here it was 20, you'll keep it as 20. Otherwise, you'll update this thing as 30. Then you look at 1/4. So 1/4 is this one. So you had 10 here and then 60 here. So you put the 70 here. And then you have 2, 3. Still is 2, 3. Have this thing. So here you have a 30 and here you have a 70. So you'll have 100 here. Just look at the previous one. So if the weight here is 30, it will be not the weight exactly, it's the time here. So it's 30, you'll have 100 here. I hope you guys understand what I'm saying.
Yes, ma'am.
And then you look at the 2/3, the 2, 3, 1. We've already covered this. Then 4, 5. So for 4, 5, you have a 70 here. You get a 120 here. And then for 4, 6, it's 70. You get a 85 here. And then for 6, 5, you get an 85. And then a 30, which will give you 115. So you cancel this and write 115 instead. So this is one iteration done. You have to do 4 iterations, n minus 1 iterations. One iteration is done. So at the end of first iteration, what you get is, at the end of first iteration, you get these things, right? Then you perform this thing again. I'm not writing what you're getting here. You can write the time here if you want to make things clear. And then you start the second iteration. So you again start from 0. Now what you do is, this is 10. So you put a 10 here. And then this one's, wait, give me a minute.
Ma'am?
Audible, right? Am I audible?
Yes, ma'am.
Yes, ma'am.
Ma'am, I have a question, ma'am.
Yes.
Ma'am, is there any difference between SPFA and Bellman-Ford algorithm?
It's the SA. It's Bellman-Ford algorithm, and the one that you're talking about is in Freud ones, right? Freud algorithm, Freud version one.
Yes, ma'am.
That there is a,
Shortest part, first algorithm.
the SP one that you're talking about is in the fluid Walsh's method, and that's obviously different from this one. It's for this is for a this is to find the minimum time or something, the minimum weight from a given vertex to all the other vertices. And then the one that you're talking about, it is for all the pairs. So it's for the minimum distance from here to here, here to here. It's for all vertices pairs. Is we'll discuss it later. Let's just get done with this one first. So for the second iteration, what you do is you again start from here. So it's 0 here, and then you do the 10 thing here again. So you get a 10 here. So it remains 10 here, nothing changes, and then this one remains 30. This one remains 80. So because this 80 is not going to change anything because you have something better here. You have 30 here, so 80 is not going to change this. And then what you do is you repeat the same thing for all the edges that we just did. In a similar manner, you repeat everything. So when you start from here, you look at 0, 1 first. So this will be 10 only. Then you look at 0, 2. This will be 80, but there's already a smaller amount here, a smaller time here. So you keep it as 30. Then you look at 1, 2. So 1, 2 is here. So this will give you 30, and this is already 30, so don't need to change. Then 1, 4. From 1, 4, you get 10, and this is 60. So it will remain 70. So this example that we've chosen, it's the things are not changing at all here. Because in the very first thing, what happens is, because all first thing that you need to see is all the weights. We've taken everything. Okay, we should have taken something negative. If you take this thing negative, then things will change. So what happens is in this Bellman-Ford algorithm, because it's particularly for the negative weights, can work for positive weights too. But if you do this Bellman-Ford algorithm and the other one was Dijkstra algorithm, it's the same for positive weights. For positive weights, if you do Bellman-Ford or you do the Dijkstra algorithm, they'll give the same answer. And for negative weights, the Dijkstra algorithm is not applicable. Only the Bellman-Ford works there. So if you have a negative, so just got the answer in your first iteration. You don't have to do further iterations because you'll get the same thing over and again. You figured out everything in the first iteration. Even if you'll keep canceling things, you'll get the same thing. That's why we're not getting in the second iteration, you'll get the same weights. In the third iteration, you'll get the same weights. So you'll do it 4 times. If you have a negative weight here, so let's just consider that thing. Let's just take a simple graph so that it's easier to understand. Let's just say this is 1, 2, 3, and this is 4. And you have this thing, say. So you have a -2 here, a 3 here, a -4 here, and a 5 here. What happens here is, in the first iteration, if you start from here, this will be at 0, then this is at -2. This is, and then you go to this one, so -2 and 5 will be -3, right? Sorry, +3. This will be 3. And then So you just write down the edges first. 1, 2, 2, 4, 2, 3, and 3. These are the edges, and then you do everything along these ones only. So for 1, 2, you change this thing, and this will become -2. For 2, 4, you will get a, this is -2 here, and this is 3 here. So you'll get a 1 here at 4. For 2, 3, you'll get -2 plus 5 plus 3. For 3, 4, you'll get 3 and 4. This is 3 and -4. So you'll get a -1. So from here, you get a -1 and you have a 1 here. So you get a better time here. Not time exactly, you get a better weight here, a lesser weight here. So you replace it with -1 and cut this thing. This is first iteration. But first iteration, you have these things. And then at the second iteration, what you do is you start again from here. Start from here. And then there's a 0 here. You'll get a -2. So at 1, 2 edge, you'll get a -2 here. At 2, 4 edge, this time, it doesn't matter because all the edges are directed to 4 edge. Okay, let's just see. Okay, the second iteration, you'll have a -2 here. Then for 2, 4 edge, you'll have a -2 plus 3 plus 1 here, but -1 is better, so let's just keep -1. Then for 2, 3, you have -2 and 5, so this doesn't change, it remains +3. And for 3, 4, you'll have 3 and -4. You don't have an edge from here. If you had something, I'm not able to find a fit example that would help you use the Bellman-Ford, because the Bellman-Ford method better, because it's also done in one iteration only.
Ma'am, I didn't get it, the negative one.
What?
Ma'am, this case, when the negative comes, the case is still.
What you just do is you just look at the edges, and then when you look at 1 and 2, so this is a minus. Okay, this is at a distance -2, so you put a -2 there. 0 and -2, so you get a -2 there. And then for 2, 4 edge, this is 2, 4 edge. So -2 was already here. And then you add a 3 here. So you get a +1 here, which we initially wrote. +1. And then for 2, 3 edge, you get a 5. You have a 5 here. -2 is already there. So you get a +3 here at this one. Then you do the 3, 4 parts. So this one, subtract 4 minus 3 minus 4. So you get a -1 here. This is your complete first iteration, because -1 is lesser than 1. That's why you cancel 1 and write -1 here. This is first iteration. And then when you do the second, in this case and in the previous one, the second iteration leads to the same thing here. So it's not changing anything, but there are cases when you will keep getting different weights until you're done with 3 iterations. But after 3 iterations, the weights will get fixed. So then there won't be any change. So what I'm trying to say is, after first iteration, you have these weights, right? -2 here, 3 here, and a -1 here. These are the weights after first iteration. Then you do this. In this, it doesn't change, but in other examples that you will be given, the weights will change after the second iteration. And then you do the third iteration. So you can only do 3 iterations here. So if the Bellman-Ford method actually works here, you will get, after 3 iterations, you'll get the same things. So your weights will get fixed after third iteration. On fourth iteration, you get the same weights, -2, 3, -1, 0. Then on fifth iteration, you'll also get the same weights. So after n-1 iterations, where n is the number of edges, your weights will become fixed at each edge. Is this fine?
Ma'am, in this, the distance was in 2 and 3, did not distance. You have written 5 here. Ma'am, can you please scroll up a little bit? Ma'am, in 2, you have written -2, and in 3, you have written +3. So, you check it in this way, that what is required to get it 5. Means into what we have to add to
No. You just add these two things. -2 is the weight here, and then you add this thing here. -2 plus 5, and you get a 3 here.
Okay, ma'am. Okay, ma'am.
Just keep adding things. first iteration, and after n minus 1 iteration, the things will become fixed if you can, if, and then you will get an answer. But sometimes what happens is after n minus, even after n minus 1 iterations, the weights keep changing. So when does that happen? That happens when you have a cycle, and not a cycle when you have a negative cycle. So this is a positive, in this case, it's a positive cycle. Positive cycle in the sense the weight here is 5, here it's 3, and then minus 4. So the sum is 4. So you get a plus 4 here, the complete weight of this cycle. So it's a positive cycle. But let's just say if it was minus 10 here, then you get a negative weight of this cycle. So if you get a cycle in a graph where there's a negative, the overall weight is negative, then you can't use the Bellman-Ford method either. In fact, you can't find the minimum weight there. The shortest distance or shortest whatever you're trying to find via using this method, you can't do that if there is a cycle with negative weights. And you won't be given, most likely you won't be given questions on that. So one thing that the Bellman-Ford, is the Bellman-Ford method clear? Because we've done only one iteration, there are other iterations. You perform in a similar way, you perform n minus 1 iterations. Is this part clear? We can do the example in the next class. I just wanted you to know the method of Bellman. Is the method clear?
Yes, ma'am.
Okay. So you can't use the Bellman-Ford method, or in fact, you can't find the shortest distance from a single source point to other points, other vertices in the graph, if you have a negative cycle.
Ma'am, this method is also evaluated by drawing table, just like the previous algorithm.
You don't need the tables here. It's actually better without a table. But you can do it with tables too.
Okay, ma'am.
So the negative cycle is, if you find a negative cycle, so if you find a negative cycle, you can't actually come to the solution of the graph. Solution of the graph in the sense, what we're trying to do here is we're trying to find the shortest time or whatever you have, shortest thing. In the previous example, we had time, but whatever the weight is, you need to find the shortest of that from one given source to every other source, every other vertex. So you can't do it using, you can't find it if you have a negative cycle, because each time you have a negative cycle, your weights keep getting reduced. We're not getting into that thing right now. If you have negative cycles, you won't be given negative cycles. But how do you detect negative cycles? You want to detect if there's a negative cycle or not. So your Bellman-Ford method, Dijkstra's method does not help you to detect if there is a negative cycle. But in fact, you can't even use Dijkstra's method when there are negative weights. You'll have a negative cycle when you'll have a negative weight, and you can't use Dijkstra's method when you have a negative weight. So Bellman-Ford method you can't use when you have negative weights. But what you can do is you can figure out that there is a cycle with negative weight. So if you get, what happens, we just discussed this, after n minus 1 iterations, all the weights here gets fixed, right? But if even after n minus 1 iterations, even so, even after the n minus 1 iterations, your weights don't get fixed, that means that you have a negative cycle. That's why your weights are not getting fixed and they keep reducing and you keep getting a better answer. Is that all right?
Yes.
Did we discuss this thing in some other lectures, or because there are not many students here either?
Yes, ma'am, and it's already beyond 10:20.
Let's discuss this in the next class then, whenever we'll have it. Okay. Thank you everyone for joining.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.